Okay, in this video we're going to look at rectifying an alternating current supply. I've turned the frequency down really low on my alternating current supply. It's about 5 Hertz right now, and you can see that the light bulb is flashing. It's supposed to be flashing. You can see as the electrons oscillate, speed up, slow down, as they're passing through the 0 on the x-axis, there is no current, no voltage, and you get flashing lights. It doesn't matter which direction they go in though, you'll get bright lights. It doesn't matter which direction they go through a bulb. If I turn my current back, my frequency back up, you can see that you no longer see the flashing because our eyes can't perceive frequencies around 60 Hertz. But sometimes alternating current supplies aren't useful. Your phone runs on a direct supply, current supply, and you need a direct current supply to charge it. So rectification is turning your alternating current supply, the sinusoidal up and down motions, the electrons oscillating back and forth, into a direct current supply. So as a recap, electrons and AC are going back and forth, oscillating around an equilibrium position. And you get the AC power supply or AC graph as they do that. The way to rectify it involves this little guy here. This is a diode. A diode has infinite resistance in one direction. That means current can only flow in the other way. So current can only flow from positive to negative. The triangle shows you the direction of current flow. You do need to remember the symbol, and you need to remember that current can flow this way. It cannot flow that way. It's got infinite resistance in the reverse bias direction. So this is my diode. I'm going to put this diode, I'm going to do a half wave rectification with a single diode. With a single diode, it goes in series with the load. I will show you the circuit once I've connected the circuit. But hopefully you can sort of see the new path. I'm no longer getting an up and down motion on this, the diode in the direction I've connected it. I'm just getting the down. Down, break, down, break. What the electrons are doing now, they're moving, stopping for half a cycle, moving forward, stopping for half a cycle, moving forward. That is a direct current. Doesn't matter that they are stopping, they're still only moving in one direction, they're just doing it periodically. Move, stop, move, stop, move, stop. With that is my half wave rectification. The way I achieve this is my AC power supply, a diode, and the load. I've used a bulb. Most of the time it will be a resistor in the circuit. That's a single diode in series with the load. Single diode in series with the load, and then I've got a voltmeter here obviously measuring my power supply. When I do that, it's going to draw something opposite than what we've seen, but you get the half wave, rests for half a cycle, half wave, rests for half a cycle, half wave. Yes, it can be negative. That would be because I've connected the diode in the reverse bias. So if I've said the electrons are moving that direction, if I connect the diode backwards now, I'll get the opposite half-wave rectification, positive half-wave rectification. Now the electrons are doing move, break, move, break, move, break, move, break. That's half-wave rectification. Not brilliant because every half cycle I'm not getting any current. You can see my bulb is a lot dimmer here, so my power is a lot less. The voltage when it wasn't connected, it was 4 squares earlier. Now it's like 1.5 squares, so that's 3 volts. It's gone from having 4 to 3 volts peak voltage there. But that is my half-wave rectification. I can use a full wave or a bridge rectifier to get a full wave rectification. In my bridge rectifier, I have 4 diodes connected in a specific way. So you can see here, I've got my power supply over here, connected at the top and the bottom. They can swap which way they do on the diagram, so always check the diagram, look at it critically. But here I've got, if I were to say the current is going to flow up and around, which it will do every half a cycle, it can only flow through this diode and then out to the load. It'll go through the load, which will be my bulb. It'll come back, and here it's going to come back from the load, and it'll flow here. It's got a choice of which diode it can go there, but it's not going to go this one because the current's flowing this way in this half cycle, so it won't flow that way. But it can flow here, and it will flow back to the power supply. So every half cycle it comes up, through the load, back up, down here, back to the power supply. The next half cycle, it'll come down, come around, come up here. It can only flow through this diode. Oh, it goes out to the load in the same direction. It's always going to go out to the load that way. At no point is this current going to change, the one coming out. Either way, these two diodes are pointing that way. So it comes through the load, back up, back in here. Now it can flow through this diode up because there is no current flowing through this one, and it goes that way, back in. So every half cycle it'll go down, through the load, back to the load, blah, 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 up here and around. So when I connect this into my circuit, remove that diode. So to the AC power supply in to my bridge rectifier, to the load, from the load, which is my bulb, and now I get this pattern. See what I mean with the shutter speed where you can't really see it? But what we're seeing now is all peaks. There are no troughs. All of those diodes are making it go all peaks. I don't have the breaks, or I got a little tiny break there, but I don't really get the breaks in between them. So what my electrons are doing now is this, 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 this. It's not like DC where it was continually going, because they are going like from 0 speed, accelerating max, stop, stop. So it is that they are doing this. You aren't getting that full straight line of a direct current, but you're getting more peaks there. So this is full wave rectification. The circuit that I've got here, my AC power supply, my 4 diodes. You do need to know the setup of the diodes. When it comes from the power supply, it needs to be able to flow both ways, to the load, to the load. Oh, I don't feel like this diagram's correct. Or they both need to be going towards the load. This diode is drawn wrong. No, I think that diode is drawn correctly. Everything on my PowerPoints will be correct because I won't have drawn them really quickly. To the load, so here, where the load is, the circuit with the load, I'm always getting a direct current. Through the diodes, it will switch back and forth, but because of the setup of the diodes, it will always give me a direct current through my load, through my thing. So my CRO that is connected here gives me my full wave rectification, and I get peak, 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 and so on. But I'm still not getting a direct current, which is a straight line. What I can do there is use another circuit component to smooth my peaks, to try and make them flatter and drop less to 0 each time. The circuit component I'm going to want to use there is a capacitor. With my capacitor, it stores energy, does not store charge, but it stores energy. It'll have the same potential difference as what the AC power supply is given to it, but it'll store it. But as it gets to this bit, it's going to discharge. It's going to let that potential difference push the current, make the capacitor discharge. I have to put the capacitor in parallel with my load. So I'm going to put a capacitor in parallel with the load. So this is my capacitor. This is a little 100 microfarad capacitor. Might want to actually be able to see the oscilloscope when I put the capacitor in. So capacitor. In parallel, so just across the bulb. You didn't see much of a difference. It has, like bottom bits of these are not at 0 anymore. They have gone up a little bit and the shape is a little bit different. But this is only 100 microfarads, so it doesn't have that much of a capacitance. If I add in parallel with the other capacitors, I'm going to shove them both in the same crocodile clip and that will make them be in parallel. So this is a 330 microfarad capacitor, hopefully. you can see a little bit more smoothing, or the shape has changed a little bit more. It's gone even further away from 0 up, and that shape is a little bit more smoother. I've got another capacitor I can try and see if we get an even more noticeable shape. So this is a 470 microfarad capacitor. Hopefully connecting it in the right way so that I don't break anything. There we go, and you can really sort of see now. So there was the 0 line, it's no longer touching the 0 line, and it's a much flatter and smoother. So the more I increase the capacitance, I got 3 in parallel there, the smoother it gets. So increased capacitance equals a smoother direct current. So then I can add in try and get that straight line that I get from an actual direct current source, like a battery. So you can see now, I've got my 4-wave rectification. My low capacitance one didn't go down to 0, but it's still going like that. That was low capacitance, you can't even see that. My high capacitance, it still does this bit here, flashes down, flashes down, goes down, and it's more of a straight line. So this is it being smooth from high capacitance. And that is rectifying, turning AC into DC.